Good morning. We are going to start with a new chapter today. So far, we have concentrated on external flow, that is, the flow which is taking place outside of a flat plate, outside of an object, and so on. But there exists a very important heat transfer which takes place when a fluid flows through, let's say, for example, a tube or a pipe. So that is collectively called as internal flow, and many of the heat exchanger designs require a thorough knowledge of what happens for flow and simultaneous flow and heat transfer inside a pipe or a tube. So these internal flows appear in the design of many heat exchange equipments. Let's say, for example, which we would see later on, something which is called a shell and tube heat exchanger. We would discuss shell and tube heat exchanger in detail in the coming classes, but what a shell and tube heat exchanger looks like is there would be a number of tubes which are going to be connected to a plate. So, through these tubes one fluid will flow from one side to the other side. If I draw this, as I said, we will do in more detail later on, but a shell and tube heat exchanger would look something like this. So, there would be a head which is attached at this end, and there would be something which is called a tube sheet which would form the region where the tubes are going to be attached. So, this is another head at the end, and we will have tubes that are connected from one end to the other. Okay, so let's draw just two tubes to keep the figure simple. So, these are two tubes, and through which the one liquid will flow in this direction. So, this fluid is going to come to the head. I have drawn this head too large, but what is going to happen is once it enters the shell, then it is going to get divided equally in the ideal design into all these tubes, and these tubes can be numerous depending on your application. There can be hundreds of such tubes attached to it. So, this liquid will come outside and will again be collected from over here. So, the liquid, the tube side liquid, let us call it as liquid tube, this is going to be taken out over here, and there is going to be another source of liquid which would flow through this and will come out from the top, and it is going to take a tortuous path because there would be certain barriers in here which would force the liquid to take a tortuous path. So, the path of the liquid which is coming into the larger body which is called the shell, it is going to go like this, interacting with the tube and ultimately come out through this outlet. So, this region is called the shell, and as you can imagine, these are called the tubes. So, since you have a large number of tubes and maybe one or two shells which I will show you later. So, these are called shell and tube heat exchanger. Shell and tube heat exchangers. Now, what happens in shell and tube heat exchangers? This is one of the most efficient way to transfer heat from one fluid to the other. So, let us say we have a hot fluid which is this is shell side liquid, and this is the liquid which comes out of the shell, and let us say the temperature of the shell side fluid is greater than the temperature of the temperature of the tube side fluid. So, the shell side fluid, as it flows over the tube, there is going to be no direct contact between the liquid, between the tube side liquid and the shell side liquid. So, the heat transfer is going to be external flow over the outside of the tube surface, conduction through the tube material, and finally, it is going to be internal heat transfer between the hot wall and the liquid which is flowing in it. So, the liquid which is in internal flow inside the tube is going to exchange heat with the shell side fluid which is in external flow. So, if you consider the tube material, the wall of the tube as the deciding surface, then the tube side wall confines the liquid which is flowing through the tubes. So, it is going to be an internal flow, and on the outside of the tube material the flow is external. We have studied external flow so far in our treatment. So, what we are going to do is we need to know what would be the relations or correlations which would give me HI. HI being the convective heat transfer coefficient on the inside. So, if you again think of the tube in contact with a fluid on the outside, that is on the shell side, then there are three resistances. The three resistances which would dictate the total flow of heat from the hot shell side to the cold tube side, they will consist of H0, where H0 is the convective heat transfer coefficient on the outside of the tube, HI which is the convective heat transfer coefficient based on the inside of the tube, and the conduction resistance which is the resistance to conductive heat transfer due to the material of the tube. These three resistances are in series. So, 1 by HI plus 1 by HO plus the conduction resistance would give me what is the overall heat transfer resistance for flow when we have this heat exchanger, shell and tube heat exchanger. So, it is extremely important to know how to express HI in terms of known parameters. So, what would be the value, what would be the expression for HI in laminar flow and in turbulent flow? So, depending on the flow rate of the fluid which is flowing through each of these tubes, I can calculate the Reynolds number. And when I calculate the Reynolds number, and if I have a relation or correlation, that should give me the value of HI. Then HI with HO and the conduction resistance, which would depend on the material of construction of the tube and the thickness of the tube, I should be able to find out what is the overall overall resistance, and from that overall resistance we would be able to obtain what is the overall heat transfer coefficient. So, it is not HI, it is not HO, it's going to be a combination of all these three resistances, inverse of which would be the overall heat transfer coefficient. So, this simple example and the application of these heat exchangers are in various areas, from the very large process plants to small units where you would see this type of shell and tube heat exchangers. So, we will talk about the design of shell and tube heat exchangers and the calculation procedure and so on, but I think the importance of knowing internal flow is very clear based on the discussion so far. So, we would start with internal flow. Now, when we start with internal flow, the first thing that one needs to see is when a flow approaches a tube or a pipe, the flow is uniform. That means it's coming with a velocity which is a constant, and the moment it enters the tube, the viscous interaction of the moving fluid with the stationary solid wall would start to reduce the velocity near the wall, while near the core, this region still does not know that a solid plate, solid wall exists over here. So, they will follow with the constant velocity over here. So, that means inside a certain inside a distance, certain distance inside the tube, the flow is going to vary with r, where r is the radius. So, this is your this is your r direction, and the total distance, total overall total radius is capital R. So, in this region, the velocity, if this is my x direction, then my V x is a function of r, but between this point and this point the velocity is a constant. As you move progressively inside the tube, this region where the velocity is constant will keep on decreasing, and the effect, the viscous effect of the wall would be felt at greater depths of the fluid inside the tube. So, a boundary layer is going to form. Inside the boundary layer, the flow is going to be viscous. Outside the boundary layer, as per our definition, the flow is inviscid. So, the thickness of the boundary layer will keep on increasing, and at some point we call it as the hydrodynamic entrance length. At some point from the entrance, these two boundary layers will coincide, and from that point onwards, if it is laminar flow, the velocity profile is simply going to follow the laminar velocity profile. So, previously you had a variation and a flat region, but over here, as you know from your fluid mechanics, it is going to be a parabolic distribution of velocity. This hydrodynamic entrance length is therefore very important, because once you cross this hydrodynamic boundary, hydrodynamic entrance length, from that point it is called fully developed flow. So, in fully developed flow, the entire fluid mass is experiencing the viscous forces, which allows you to derive the functional the dependence of the velocity with r, and we all know that it is going to be parabolic in nature. The and of course, what would be this hydrodynamic entrance length is something very important. You would like to know what is this entrance length. Now, this entrance length is definitely going to be a function of Reynolds number. So, if you keep on changing the value of the Reynolds number, the hydrodynamic entrance length would also vary, because more the value of Reynolds number, you are going to have better transport, more transport of momentum through the fluid towards the core of it. So, there is definitely should be a dependence of the entrance length on the flow Reynolds number, and the flow Reynolds number is defined in terms of a length scale, which is the diameter of the tube, and the properties which are mu and rho, viscosity and density, and some sort of a velocity. So, what is the velocity to be used in this case? The Reynolds number for flow in a pipe is always expressed in terms of the mean velocity. Let's say we denote it as um. So, your Reynolds number expression should be rho um, then d times mu, where d is the diameter of the tube and mu is the viscosity. So, we also know that the expression for the entrance length for laminar and turbulent flow are different. So, I am simply, for completeness, though you have studied these in your fluid mechanics course, for completeness I will simply write those relations which were obtained for laminar and turbulent flow, what would be the expression for the entrance length. So, for laminar flow, this entrance length, which is called HFD, the length which is required for the flow to become fully developed. So, that is the significance of the FD term divided by D, where D is the diameter. For the case of laminar is about 0.05 Reynolds number based on diameter. So, the entrance length can be expressed as a function of Reynolds number and this entrance length is non-dimensionalized with the diameter of the pipe through which the flow is taking place. And for turbulent, for x by d greater than 10, it is assumed flow is fully developed. So, the two relations that are generally used, this one is for laminar, that is x f d by d is 0.05 Reynolds number, and for turbulent, if x is 10 times the diameter, the point where you are finding out whether the flow is fully developed or not, if it is 10 times the diameter from the entrance, it is assumed to be fully developed. And we all know what is the expression for velocity. The velocity in fully developed condition is a function of r only, it is not a function of x. So, it is a function of r, but it will remain the same as you move along this. So, this would be 2 u m, where u m is the average velocity 1 minus r by r naught whole square, where r naught is the, so this is what r naught is. R naught is the radius of the pipe. So, this is the fully developed velocity profile in here. There is one more important thing in internal flow of a liquid through a pipe. You are more interested in finding out what is the pressure drop for such cases. So, the pressure drop for such cases can be expressed in terms of Moody or Darcy friction factor, which is denoted as F is minus dP dx, the pressure gradient, P is the pressure, dP dx the pressure gradient by rho u m square by 2, where u m is the average velocity. So, this is some sort of a dynamic pressure, and this is how you obtained the friction the Darcy friction factor. And when you talk about the friction coefficient or fanning friction factor, this fanning friction factor is Cf, which is wall shear stress by rho u m square by 2, and you would see that this Cf is going to be equal to F by 4. So, there are two different types of friction factor which are used in fluid mechanics literature. One is F, the other is Cf. So, the relation between F and Cf is simply going to be F by 4. There is no other difference. So, when you use Moody diagram, what you get is the Darcy friction factor, which is F. When you talk about the friction factor from fanning friction factor, it is Cf, and the relation between them, if you look at the definition carefully, it is simply going to be Cf equals F by 4. There is one more thing which I should write in the space, just to make sure that everything is going to be in one page. So, this F is going to be 64 by R e for the case of fully developed laminar flow. So, this is the relation that you are familiar with for laminar flow, and for the case of turbulent flow, the mostly it's to be used by the Moody diagram. In the for the case of turbulent flow, this is from Moody diagram, with which I am sure you are familiar with. This F is going to be 0.316 Reynolds number to the power 1/4 to the power minus 1/4 for Reynolds number greater than less than equal to 2 into 10 to the power 4, or the friction factor can be expressed as 0.184 Reynolds number based on diameter to the power 1 by 5 when RE is greater than 2 into 10 to the power 4. I am simply putting all of them in one page for the sake of completeness. And so, what we have shown here is that what would be the expression for F in laminar flow and what would be the corresponding expression for F which are approximated from the Moody diagram. So, you can either use Moody diagram directly. So, you understand the Moody, you realize, you probably remember the Moody diagram is nothing but the value of F, the friction factor on the left hand side, and on the x axis you have different values of Reynolds number, and there will be a family of curve for different values of the thickness of the inside of the pipe. So, higher the thickness, higher the roughness, so I am sorry, roughness, higher the roughness of the surface, inside surface of the pipe, for the same Reynolds number you get a high value of F. So, recollect that the Moody diagram where friction factor, the F is plotted against Reynolds number, and at higher values of Reynolds number the variation of F with Reynolds number becomes almost negligible. So, for a high value of Reynolds number, which is also known as for a highly turbulent, for a completely turbulent flow, the value of the friction factor is independent of Reynolds number. That is one of the observations. The second observation is the inside roughness of the pipe dictates the value of the friction factor. More the roughness, higher would be the value of the friction factor. So, the same Moody diagram can be expressed in terms of the two correlations which I have written over here as this for some value of Reynolds number and this for other values of the Reynolds number, for the case when the flow is taking place inside a smooth pipe. So, the results which I have drawn, the correlations that I am proposing, they are only valid for smooth pipes and nothing else. The problem comes is what we are going to do when we are dealing with thermal situations. We understand we can visualize, mentally visualize that the flow as it takes place, it is going to become independent of x, it is going to be only a function of r, and from that point onwards the velocity at any given r location is going to remain constant. If you change r, the velocity will vary, but if you keep the r fixed, the velocity is going to be the same wherever you go axially inside the pipe. So, the profile and the value of the velocity remain unchanged once the flow becomes hydrodynamically fully developed. Now, let us think of the same thing for the case of heat transfer. So, I have a tube which is being heated externally so as to maintain a constant heat flux all along the pipe length. So, as I move in this direction, when the flow comes in, the velocity is uniform and the temperature is uniform as well. As it enters, both the velocity and the temperature would start to become function of r, and as I move further and further, at some point the velocity is fully developed. So, the velocity will not change with position at a fixed r anymore. So, let us look at this figure once again. At any given r, the velocity at all these points are same when the flow is fully developed. The velocity at this point will remain same though different from this point, but it will not be a function of x. Okay. But over here the velocity could be a function of x. What happens in the case of thermal cases? For thermal conditions, since I have a constant heat flux all along the wall of the pipe, the temperature is going to change with x. So, the way we have defined fully developed flow from a hydrodynamic point of view, that the velocity at any r is independent of x, cannot be said for the case of thermally fully developed flow, because the velocity will always the temperature, the velocity at any r will remain fixed, but the temperature at that r will keep on increasing, since I am constantly getting some amount of heat from the side walls of the pipe. So, the constancy of temperature at a given r cannot be used to define a thermally fully developed flow. So, what is the definition that is generally used for thermally fully developed flow? We say that we are not interested in the value of the temperature, we are more interested in the shape, the profile of the temperature. So, if the temperature profile, or more correctly if the dimensionless temperature profile is not going to be a function of x, when the dimensionless temperature profile is invariant with x, when that condition is reached, we say that we have reached thermally fully developed flow. So, instead of a velocity, instead of a specific temperature, we say that it is the shape of the temperature profile, shape of the dimensionless temperature profile, which is relevant in defining what is thermally fully developed flow. So, I am going to write the expression for thermally fully developed flow and see how that can lead to some of the interesting results for heat transfer. So, let us start with the definition of thermally fully developed flow. So, thermally developed flow it is defined as when del x of T s is the surface temperature and T s can also be a function of x, minus T, which is a function of r and which could also be a function of x, which is going to be a function of x, since in thermal cases the temperature will always change, by T s x minus T m x. So, this becomes equal to 0. Now, when you talk about when you see these three temperatures, this is the surface temperature of the wall, which could be a function of x. This is the temperature of the fluid, which is flowing fluid, which is a function of r, that means how close it is to the wall, and it is also a function of x, where x denotes the actual position. What is Tmx? Tm is the mean temperature. Tm is the mean temperature of the flowing fluid, and the way Tm is defined is the total energy which is transported by the fluid. So, this is the total energy transported by the fluid which obviously would be equal to an integration over the cross sectional area rho u Cv T Cv T dAc. So, this is, if you look at this clearly, rho times u would give you the mass flow rate, the mass flow rate per unit area, integrating it over the entire area. So, this is m dot Cv T, where T is the temperature. So, this is the total energy content of the flowing fluid. Now, this total energy content of the flowing fluid, if we equate that with some mean temperature T m, then the definition of the mean temperature would be 2 u m r naught square times 0 to r naught UTR dr. So, the only thing that you have to do is the cross sectional, for the case of cross sectional area DSC, you simply have to write twice pi r dr, because that is the cross sectional area through which the liquid is flowing. So, the cross sectional area through which it is flowing is pi r square. So, obviously DAC would be twice pi r dr, and when you put that twice pi r dr in here and you take everything this thing out, the rho and CV which are out of the integration sign. So, this is what you are going to get. So, this gives you the definition of Tm, and this Tm is a function of x, okay, because the mean temperature of the flowing fluid will keep on changing. Let us say I have flow from this side, I find out what is the energy that is being transported by the fluid over here, and all the time it is receiving energy from the pipe walls. I find out what is the energy which is being transported by a liquid at this point. Okay. So, the energy here is definitely going to be different than energy at this point, because some amount of energy has already been added by the walls in between these two cross sections. So, the Tm, the area average temperature, the flow average temperature that you would get over here and the Tm that you would get over here, they must be different. So, Tm, the mean temperature, the flow mean temperature is a function of x, which was not happening for the case of velocity. The average velocity due to equation of continuity would remain the same between location 1 and location 2, but the average temperature between these 2 points would be different. That is what make heat transfer more complicated, and that is why we cannot say that the velocity invariant being a condition for fully developed flow, we cannot say that the no variation in temperature is the condition for thermally fully developed flow. That is why we have to bring in that the shape, the dimensionless shape of the profile will not be a function of x. That is the necessary condition for thermally fully developed flow. So, let us expand this expression and see what additional information we can obtain out of this. So, this is this is the definition, and this being 0. So, the temperature ratio therefore is independent of x, and the derivative. So, if this temperature ratio, that is the expression inside the third bracket, since it is independent of x, then it must also be independent of r. The temperature ratio is independent of x. So, the derivative of the ratio with respect to r must also be independent of x. So, what I mean to say is that if I write it in this way, that is T s minus T, I am just dropping x r etc., but they are the same as before, by T s minus T m. I simply dropped these things to make it more compact. This obviously can be expressed as minus del T by del r at r equals r 0 by T s minus T m. This cannot be a function of x. The derivative of the ratio, the x derivative of this is equal to 0. So, therefore, the r derivative of the same ratio cannot be a function of x as well. So, if this is not a function of x, since the temperature ratio is independent of x, so if I take the r derivative of the temperature ratio, that will also not be a function of x. I would repeat it once again. I have defined dimensionless temperature, which is T s minus T divided by T s minus T m. I take the derivative of that with respect to x, and that is equal to 0 as per our definition. So, that means the dimensionless temperature which I have defined is independent of x. That is why its derivative with respect to x is 0. Now, if I take the r derivative of the same ratio, that r derivative of that would also not be a function of x, since the ratio itself is not a function of x. So, if I take the derivative of that ratio with respect to r, a, b, c, etc., it does not matter, the r derivative or any other derivative of that will not be a function of x. That is what I have written over here. So, let us look once again to the expression that I have written at this point, which is simply this, and in order to obtain over here, I am using Fourier's law, which says minus k del t by del y at y equal to 0. When you transform the coordinates to r, it is del t by del r at r equals r naught. So, if this is the pipe wall, then this is your r and this is your y. So, at y equal to 0 transforms to r equals r 0, y equals 0 is r equals r 0, and since y and r are in opposite directions, so I absorb the minus sign when I change the variable from y to r. Okay. And q double prime s, which is the heat given to this wall, must be equal to H times T s minus T m, that is Newton's law of cooling. So, this is Fourier's law and this is Newton's law. This is in terms of the conduction which is taking place, this is in terms of the convection which is taking place from the pipe wall to the inside. So, when you put this over here, what you would get, the important relation is H by k is not a function of x. So, when you put del t del r in here and from the Fourier's law and T s minus T m from the Newton's law, the q double prime s will cancel out from the numerator and the denominator. What you are going to left with is H by k is not a function of x. So, an extension of this is H is not a function of x. This is extremely important. K is a constant physical property. So, k is, since k is a constant, what I see from here that H is not a function of x. So, one of the important statement of the thermally fully developed flow is that the natural convection heat transfer coefficient H is not a function of x in the thermally fully developed region. So, what we have now then obtained is a way to define what is thermally fully developed flow, and in order to do that, we have expressed it in terms of a dimensionless temperature, and we took the x derivative of that del x of that ratio equal to 0. We say that this is the condition for thermally fully developed flow. That means, the flow, the shape of the temperature profile will not change with x, and a direct corollary of that is that the variation of this ratio with r can also not be a function of x. When you do that and when you substitute Fourier's law and Newton's law into that expression, what you get is that the heat transfer coefficient, the convective heat transfer coefficient is not going to be a function of x. So, the important property of thermally fully developed flow is that the convective heat transfer coefficient remains invariant with the axial position once you establish thermally fully developed condition. It would not be true in the entrance region, but once you are in the thermally fully developed region, H is not a function of x. So, in the next class we will see what other interesting results one can obtain, ultimately leading to the relation or correlation which would give me the value of the heat transfer coefficient for internal flow based on whether it is laminar flow or turbulent flow and so on, such that I can make the complete calculation of overall heat transfer coefficient in such heat exchange devices.